with recording. This is actually everything you've been doing in 4.1, 4.3, 4.4, which you'll be quizzed over today, but it's now with word problems. You know, and it's funny because students always say, I don't like word problems. I love word problems because finally, where would I use this type stuff? So the situation is I want to maximize something or minimize something. So in this case, we have a box, and it's an open top box. We want to make it out of 12 by 12 tin sheet. What size should X be to maximize the space of this box? In other words, hold as much as possible. Now, probably this would have been a little bit more difficult if they wouldn't have drew this for you. So if you can see on the picture, what X is where you're cutting it and folding up the corners here. Those are the corners, and you're folding up these sides. So if it's 12 by 12, if this is X, a corner, this is X, a corner, then it would make sense that this little piece here, the side, would be 12 minus 2 X's. And then, of course, this is square, so this would be 12 minus 2X as well. So basically what I want to do is I want to maximize the volume. I mean, that's what I'm doing. So as soon as you see something like, says to maximize something, then you know right away, oh, we're going to get derivatives, we're going to set it equal to 0, find critical points, and all that kind of stuff. The problem is there's no equation. Well, we can make an equation because this is a box. So my volume then equals the height times the length times the width. And so back looking at that picture, the height then would be X. Okay, those were those corner pieces. And then the length would be 12 minus 2x, and the width, same, 12 minus 2x. So now we have a function that I can find critical points for. Again, you could have at it new product of a product rule, not me. I'm going to multiply all this stuff out. So of course this first piece is going to be 144 minus 48x plus 4x squared. So all I did was multiply that. Now I'm going to distribute the x. And I'm going to go ahead and just turn this around how we're used to seeing the largest exponents first. So I get 4x cubed minus 48x squared plus 144x. Now, on your quiz today, there's no restrictions. What I mean by restrictions is domain restrictions. And I probably shouldn't have told you that because now you know the answer to what is the domain is. All real numbers. So I give you that one away. But this one has restrictions. And so my question to you, and if again you visualize that box, so we had X, we had 12 minus 2X, and we had X, this side. And this is a 12 by 12 box. What would the domain restrictions be of this? Don't all answer at once. I'll give you the left side. It would be kind of silly to say that X could be equal to 0. You know, that'd be kind of small, right? Would be nothing. But what would it have to stay below X? 6. Very good. Because in other words, if this piece is X, this piece is X, and again, it's kind of silly to say it could be 6, but it could, is we're just saying that would be the whole corner. Okay, so if I had 6 plus 6, that's our side of 12. Very good, Alfonso. All right, so, and the reason, I hit undo and didn't mean to, the reason that I said this doesn't matter today is you probably remember if you did your 4.1 homework, when you found critical points, you plugged in the critical point and the endpoints into your function. Okay, so just remember you don't have to do that today. You just find the critical point. So find critical point, meaning right there is my function. So go. Tell me what's the derivative.
4x squared minus 4x.
How about 12x squared? Minus what? There you go. Plus 144. So all we did, bless you, there's that cat again. So all we did was take the derivative. this is what you'll do on the quiz today. Okay, so you'll take the derivative, you set it equal to 0, squared minus 96x plus 144. And then, of course, you always look, I mean, you could have at it and try to factor that like that if you want, but you always look to see if something can come out. And so I would factor out a 12. So I get x squared minus 8x plus 12. And then I'll do the x's. That's negative, that's positive, so they're both negative. What numbers do I put in there to factor that?
6 and 2.
I heard 6 and 2. And so then this means that my critical points, because we set both of these equal to 0, is x equals 6 or x equals 2. Once again, we kind of go back to our logic and say, well, it would really be silly and we really wouldn't have a box if we made back up here our drawing, if we made that size equal to 6. So we would pick the one that lies inside our domain. And so then they've asked, how could you maximize the volume with what value of x? So that's a critical point. Technically, you should plug in endpoints. So I take my critical point, which was 2. I plug it into my original equation because I want to know what the volume is. I plug in my endpoints as well. So my original equation was x times 12 minus 2x, and there were 2 of them, so let's just square it. So x times 12 minus 2 times x, and then x times 12 minus 2 times x. These actually become 0, which kind of would make sense. You've used the whole side, and this becomes 128. So therefore, the max volume is 128 cubic inches. And thus, the cutout should be 2 inches on each side. So again, I don't want to do something like this and confuse you today. On today's quiz, all you're doing is that, because I did not restrict the domain. How you would know, you'd have to put in, and again, these are the endpoints, is we said, are there domain restrictions? Well, of course there are, because we had a limited amount of 10 to be able to build this box. All right, continuing right along. All right, so we're going to now make some aluminum cans. So a company wants to manufacture these cans with a volume of 1,000 cubic centimeters, 1 liter. What should the radius and height of the can be to minimize? So this is a minimized problem, where the other one we were maximizing. This, they want to minimize the amount of aluminum used. So if I look at this, I can see that the top and the bottom, don't look at my bad drawings, are circles, okay? Because it told us this was a cylinder. And so my surface area that I'm trying to minimize is going to equal the top circle plus the bottom circle. And then we could call this kind of the side. If you cut those pieces off, then you can roll that out flat and you have a rectangle, right? But in this case, it's going to give us this rectangle. So the side are rectangle with height h, right there. But then our width is actually going to be the circumference. Circumference, I may got too many letters in there, you can't read it anyway. Yeah, kind of. All right, and so to find the surface area, then I'm going to add the top area, I'm going to add the bottom area, and I'm going to add this side area. So away I go, then surface area would equal pi's r squared, right, for circles, plus pi r squared, and then plus my circumference times my height. So again, that's my rectangle. How do you find the area of a rectangle? Height times width. So that's my height times width. How do you find the area of the circles? Are those pieces. So now I have an equation. The only problem with this equation is when I look at this, I say, uh-oh, I have two different variables. But what's nice is you could put this in terms of one variable. So let's do that. Put in terms of one variable. And the reason we can do this is, if you remember, we were given the volume of the can was 1,000. Okay, and we can set this equal to our volume, so pi r squared h. And so now I have an equation that I can solve this for h. So h just simply equals 1,000 over pi r squared. Okay, and once again, you see there's a lot of stuff you'd have to know. That's the volume of a cylinder. And so the only reason I did this is now I could substitute that in for h, and as you can see straight across, I don't have one variable, the radius. So I would be trying to find the change in volume with the change in radius. I can go back and then solve for the height to see what the height would be. So continuing on, so I have this S equals 2 pi r squared. I just took the two circles, pi r squared plus pi r squared, and then I had the plus 2 pi r h. And then we said, well, we solved this for h, which is 1,000 over pi r squared. So all I'm going to do is just rewrite this again. So I have S equals 2 pi r squared plus 2 pi r times h, and then there's my h. So this just makes it nice now that I have one variable, so that's why I did it. And so to make this look a little better, 2 pi r squared plus 2,000, just multiply that, and then of course the pi's cancel, and then one of these cancel, so I get 2,000 over r. At this point is where I would graph it, and you could find the minimum at this point, but let's do it the show your work way. So if I want to minimize something, I find the critical point. How do I find the critical point? Take the first derivative, set it equal to 0, and then solve for my variable, in this case r. So I'm once again finding the change in the surface area with respect to the change in the radius. So if I look at that right there, tell me what the derivative of that is. Wellington? What's the derivative of that piece? Very good. Yeah, for some reason that pi bothers. Yeah. It's just kind of like a constant. You could throw it out front and just take the derivative of r squared and then multiply the 2 out. And then plus, or maybe a minus. What's next? There you go, 2,000. So once again, I would have probably, for those of you that are, still kind of new with this, I would have brought that up to the top, brought the negative down, subtracted 1, and then I just brought it back down to the bottom. That's all I did. All right, so to find the derivative, we set this equal to 0, 0, and then we solve for r. 2,000 over r squared. You hear me say over and over and over whenever you have one fraction and something else, even if it's not another fraction, make it into one fraction. So this becomes 0 equals 4 pi r cubed minus 2,000 over r squared. What I did was get a least common denominator, which was this, and so I needed an r squared on the top, and so that's how I ended up with r cubed. All right, now as I've kind of mentioned before, this for some reason blows students' mind that you can do this. But basically what you're doing is you're multiplying r squared on both sides. That cancels and that becomes 0. Most students don't even go to that trouble. Once you get, and that's why you like to get a fraction, once you get one denominator, it just disappears. Well, it doesn't really disappear, but it's because you're multiplying it on both sides. And so now I probably would throw the 2,000 just to make it positive on that side. I would, of course, divide by, let's just do it in steps, 4 pi. And so I would get r cubed equals 500 over pi. And then, of course, my last step, I would cube root it. Now, I think when I looked at this, because this is my math lab problem, I think you had to leave it at that, okay? But I went ahead and said, well, let's just kind of see what that number was. And I got this number. I don't remember, they may have said round off, but I'm thinking they didn't. They wanted it exact like that, so the cubed root of 500 over pi. And so that tells me the value of my radius, my critical point. So I can go back and get my h. Remember, it was 1,000 over pi r squared. So 1,000 over pi times this 5.419 squared. And as you can see, which probably to some of you made sense, that if you notice the height of the can is twice the radius, okay, in this case. And technically, most of you would probably just go on and say, there's my answer, and my math lab said it's all good. But on a test, I might ask you now, we found this critical point, and my question to you would be, how do you know it's a min? Well, because they told me I was minimizing something, it would make sense, right? But you should check it. How I check it, I'll tell you the both ways to remind you. Most students like the way, Wellington, that they look at values on this side, so I don't know, 5, this side 6.
I like your way better.
You do? Finally, you've come to the dark side. And then you plug these values into what?
The first derivative?
Yes. And you plug these into your first derivative, and then, of course, if they're positive, then you know it's increasing, blah, blah, blah. If they're negative, which this one, of course, would be because it's a min. Again, I don't do it that way. And he had a really good example why, because he had all kinds of logarithms and e's, and that made me we didn't even know what number to pick over here, And so if you want to do it that way and you're good with that way, that's fine. I don't like it that way. If I can find somewhere, I guess here was my first derivative. This is the way I do it. So my first derivative was 4 pi r minus 2,000 over r squared. What I do is I take the second derivative. Of course, if it's easy to do. Now I say that, and you might say, well, I don't want to take second derivatives. Sometimes you do have to take second derivatives when you want to find what? Inflection points. So sometimes you got to do it anyway, okay? Which, hint, hint, today. So as I can see here, this is just a constant out front, so this becomes 4 pi. This, once again, if you want to do it, this is minus 2,000 r to the minus 2. So I bring the negative 2 down, I get a positive 4,000. And then I subtract 1, and I get this value. Well, I don't really have to, and then what do? Then you take your critical point, which I've already lost it, it was that number right there, and you plug it in here, and you see if it's positive or negative. Well, as you can see, that's a positive number, so you're going to get a positive number. And so it's positive, and that tells you that's a min. So again, that's kind of how I do it, and maybe it's because usually you have to see if there's an inflection point. And so, but if it's difficult to take the second derivative and there's no need to, like this problem, there was no need to, then you could do this. Just remembering you're plugging values to the left of the critical point, values to the right of the critical point into the derivative, because that tells you your slope. Okay, so whichever way you're comfortable with. So forget about them. All right, this is kind of weird and kind of funny is I have a student that's tutoring another student, and they came to me yesterday with this problem. I'm like, I just went over this in class. So this is a small island is 3 miles from the nearest point P on the straight shoreline of a large lake. If a woman on the island can row a boat 3 miles per hour and can walk 4 miles per hour, wouldn't you row faster than you walk? I don't know, I don't row boats. Where should the boat be landed in order to arrive at a town 16 miles down the shore from P in the least time? If you're like me, I pretty much quit reading up here. yeah, because freaking words. So what I do is I kind of look and see, well, what are they even asking me to do? They're basically asking me to minimize her time, okay? Where should she land this boat? So I go through and I get numbers because I figure I'm going to use the numbers. So 3 miles from the nearest or some point, she can row a boat. This is how she rows the boat. She can walk, and then 16 miles to the shore. Now, once again, if I had to take this and solve it, I'd draw a picture right away. Luckily, they did it for you. So let's look at the picture and see if we understand this. So it said there's some point P, which is 3 miles from the island. Okay, so that's that line right there would be 3. I guess the island has burnt up and that's why it's black. Maybe this is a survivor island. That's what we could do is I could put y'all on an island and whoever survives gets me for Cal 2, right? It'd be awesome. All right, and so then it says where X is the distance from the point P to the place of landing. So it probably would have been better if this would have been a different color. So the hypotenuse, as you can see here, is what she's rowing. Okay, and then it says the woman rows to the place of the landing, which is right there, and then from that point to the town would be 16. Okay, so you kind of have a visual here of everything, and so as you could probably see, well, easily I could get the hypotenuse. I know that's 3, I know that's X, so I do that whole Pythagorean thing, but then I say, well, okay, well, what again am I trying to do? I'm trying to minimize the time. So let's kind of go through some of this. And the first thing I said is what we could do is we could find the distance first. So the distance that she rows, again, is the hypotenuse. Kind of easier to say it, to see it on here. And so I just used Pythagorean theorem, did a bunch of steps. So in other words, that's your a squared plus b squared equals c squared. And in this case, I solved and took square roots of both sides. The distance she walks, if she's at that point and that whole distance was 16, then that distance would be 16 minus x. And so basically what we're trying to do is tell her where should she row to make this faster. I think she should get out of the boat and walk, right, on water, because she apparently walks. All right, and so again, we're trying to minimize her time. And that's probably the hardest part, is to figure out what are they even asking me to do. And so why did I even get distance? Because I know that my distance formula is distance equals rate times time, and I want to solve this for time. I want to put my equation in terms of time, and that's what I'm going to try to. All right. Again, this is kind of like the box. We have a domain. It would be kind of silly to say 0, the time she didn't walk at all, or the miles, and then 16, the total. So we do have some restrictions. And so here, and I'm sorry that was on the other slide as well, here I set up my function. My distance, because remember this is in time, so in other words, I take my distance over my rate. This was her rowing, and this was her walking. This is the distance of her walking and the rate of her walking. Again, why I'm doing that, that's time and that's time. That's what I want to minimize. How do I minimize it? Critical point. Okay, so you're just doing the same thing. It's just probably that was the hardest part of this problem, is getting this set up. So I take the derivative. Because there's kind of like a 1 right there, right? So I would pull that out front is all I did. And then I kept telling you over and over, remember the derivative of a square root is 1 over 2, leave the square root alone, times the chain rule, the derivative inside. And then here, again, I'd kind of pull the 1/4 out front. The derivative of 16 is 0. The derivative of negative x is negative 1. And then I would just kind of do some things to make this look a little bit better. X stays the same at the top. This becomes minus 1/4. And as you always hear me say, if you have more than one fraction. So we're just still solving for critical points because we're going to eventually set this to 0. So my least common denominator, basically what I did was my cross multiplication. So that's where I get 4x that all came to this side. And this is where I say most students do this. They just say that goes away. It doesn't really go away. What happens is we set this equal to 0 and we multiplied both sides by that, and so it canceled out, however you want to say it. And so really all we're looking for is this top up here. All this for x, going to move some things around. I threw that to the other side. And I went ahead and squared both sides because of that square root. I knew I was going to have to do it eventually, okay, whichever step you wanted to do it in. And then, of course, I distributed this out through all my steps to find. And again, I think this is one that wants an exact value, but I went through all my steps to find my critical point, okay? So this is my x critical point. And again, I want to know, is that going to minimize her time? I had restrictions, so I actually have to look at the endpoints as well. All right, so my critical points where my derivative equals 0. I got this. I have my domain restriction 0 and 16. So I want to find which one's the minimum amount. So how do you find which one is the minimum amount where she should land the boat, basically? And I plug in my endpoints, so you can see here's the 0, and you can see here is the 16. I plugged in my endpoints. I got these values and the critical point. Okay, so I plug in my critical point here as well, because once again we're minimizing time. So if you notice, all of these got plugged into the original function. And I just look to see which one's the smallest. Okay, and I don't know about you, but I don't want to do a second derivative. This is a min. I mean, why would they give me this problem if it's not a minimum, right? And again, you know, of course, you could graph it. That's probably what I would have done to check it. So kind of the order is what I see students struggle with in here. Today, the quiz, when I sit down, the first thing I would do, take first and second derivative right away. That's all I do. Set both of them equal to 0 and solve for x. Write first derivative, critical point. Second derivative, inflection point. I mean, that's how I wouldn't even read the rest of the questions. And then you can go through the, you know, where is it increasing, decreasing. I've already told you what the domain is. Wouldn't it be funny if it wasn't all real numbers and all you put that on there? But it might be. Or it might not be. If it wasn't, then that question would be worth like 87 points. What is this? 4-6. All right, so I'm going to do another example, and while I'm doing this other example, let me just say again, because probably everybody's here that's going to be here,